Hello everyone, and welcome to the first recitation of CMPS 211 Discrete Structures. My name is Al-Abbas Khalil, and I'm gonna be your TA for this course. I graduated from my master's degree in AUB last year, and this is gonna be my fourth time giving this course, so hopefully you're gonna be in good hands. Now, we're still not 100% sure how this is gonna work. Usually with recitations, I'll meet up with you for about an hour every week and we'll work on a bunch of exercises. For now, for this week, I'm gonna see you on Thursday at 5 p.m. and we're either gonna be going through this recitation all over again, or I'm gonna be answering some of your questions. So let's start. So let's run through some definitions that have to do with formulae. So when is a formula satisfiable? A formula is satisfiable if you can find at least one assignment that makes this formula true. Well, what do we mean by a formula? It's something like this. So we read this: P or not R or not S. So P, R, and S are going to be your propositions. So they're just, you can think of them for now as some variables that can either contain true or false, 1 or 0, yes or no. Okay. So this formula will be satisfiable if you can assign to those variables these values in such a way that the overall is going to be true. So for example, if we simply set P is true, the whole formula is going to be satisfiable because true or whatever, you don't care, it's going to be true. So even if R is true or S is false, whatever, it's going to be satisfiable. And another one is if you set R is false. So if we say, hey, now R is false, not R is going to be true. So same as before, the whole thing is going to be true. When is a formula a tautology? Well, it is a tautology if it's true for whatever assignment you give it. It's always going to be true. So this thing is not a tautology. Why? If we do this assignment, so P is false, R is true, there you go, not R is false. And finally we have S is true, not S is false. So the whole thing equates to false. There you go, doesn't work. However, this thing is a tautology because for whatever assignment you do, it's gonna always be true. So if P is true, then true. If P is false, well, not P is gonna be true, the whole thing is gonna be correct. This thing is not satisfiable. For whatever value you give P, and for whatever assignment you give the formula in general, it's always going to be false. So you can't find an assignment that makes it satisfiable. Alright, let's see if the following is satisfiable or not. So this is what we call a disjunction. So if you notice, everything inside the brackets is separated by ors, and between the brackets we have ands. So inside the brackets, it's enough for just one variable to be true and the whole thing is going to be true, but you want all the brackets to be true. So you want to evaluate this to true, this to true, this to true, all, and so on. Well, step one, what you could do is try to find the variable that's like most occurring, which in this case is gonna be P. Okay. So if we simply set P to be true, all of these guys are no longer a problem. and you're left with this guy. Well, we said P is true, so this guy is now going to be false. We're left with these two. You can assign whatever you want. So if you say Q is false, now Q is going to be true. So this is also going to be true. And just as a remark, if you haven't figured it out already, true or anything is going to be true. False and something, whatever it is, it's going to be false. False or something is going to be that something. Okay? And as you can see from here, true and something is also going to be that something. Okay. Now, a big part of the recitations is you guys have to try and solve the problems. So whenever there's a part that comes that I expect you to solve, I'm just gonna put this pause button on the upper right, just so you can know, okay, you have to now solve this, and I'll give you maybe a few hints about the problem, then I'll say, hey, pause the video and try to solve it yourself. So, similarly, we wanna see if this guy is satisfiable or not. But instead of doing what we just did, I want you to try out these 4 assignments. So you can pause here and try to solve it. Okay, so the first one is not gonna work because P false, so this guy is false, Q is false, S is true, there you go, not S is false. So all of this is gonna equate to false. And false and anything is just gonna be false. So this assignment doesn't work. It doesn't make it satisfiable. Same thing for the other one because of these guys. And the last 2 will work. If you run these, they will simply work. So yeah, it is satisfiable. Okay. Let's run through some more definitions. Zoar nands and implications. Okay, starting off with Zoar, we're going to be comparing it with the normal OR. So this normal OR, we usually say it's inclusive, whereas the other one, we say it's exclusive. We'll see what that means in a bit. So let's start with the normal OR. You have statement A says X likes Germany, and X can be just some person. And statement B says X likes Mexico. Let's assume X is the same person. Let's say X is you. So you like Germany, you like Mexico. Well, in the first possibility, remember 0 means false. In the first possibility, if you neither like Mexico nor you like Germany, the statement is going to be false. You don't like either of them. Let's say you only like Mexico. Well, the whole statement is going to be true. Do you like Germany or Mexico? Yes. Let's say you like Germany. Do you like Germany or Mexico? Also yes. And hey, if you like both of them, the statement is also going to be true. Okay. So in the normal OR, it's inclusive. If you like one of them, the whole statement is going to be true. Whereas if we go to exclusive, you want one of them to be true, but not both at the same time. Okay, so the difference is here. In exclusive OR, if both of the values are true at the same time, then it's gonna be false as a statement whole. You only want one of them to be true. So for example, let's say again this person is you, and your ID is this thing, and your ID is this thing. Well, if your ID is really this 9999, then the equation is going to be true. And if your ID is the other thing, it's also going to be true. But as we know in AB, you can't have 2 different IDs at the same time, 2 different student IDs at the same time. So both of these existing as a fact together is false. There you go. It's going to equate to NAND is just not AND, not AND. So the normal AND, it's only gonna be true if both of your elements are true at the same time. So not AND is gonna be the opposite. It's true in every other case, but and false in the only case where X and Y, A and B, whatever, are true at the same time. All right, now implication. This is one of the important ones, and it reads like this. We're saying if P, then Q. So if you start off with P, like as a premise, then you should reach conclusion Q. Okay, let's see an example of this. Let's say if at the end of the semester you get more than 85% as an overall grade, then you'll get an A on this course. So if you get more than 85%, that's like your premise. You'll reach a conclusion where you're gonna get an A. Okay, so that's like a rule, let's say, that's been given. Well, there are 4 possibilities as we see in this truth table. Okay, let's just run through them. Let's start with this one. So 0, it's false. So let's say you don't get more than 85% at the end of the course. P is false, so you got less than 85%. And Q says you didn't get an A. Well, this equates to something that's true. It makes sense. You didn't get more than 85%, so you didn't get an A. There's nothing wrong here. Okay, the other one. You still didn't get more than 85%, but you did get an A. And that still makes sense. That's still something that's true. If you start, if your premise is false, that doesn't mean your conclusion has to be false as well. One of the conditions said you have to get more than 85% to get an A, but it wasn't the only condition. The third one, you start off with the premise is true. You did get more than 85%, but you reached false. You didn't get an A. This is where it doesn't make sense, because you did abide the rule, you got more than 85%, but you didn't get an A. This is the only place where it's gonna be false, like something doesn't make sense. And finally, you did get more than 85%, you did get an A, everything makes sense. Okay, so the takeaway is with implication, it's always going to be true unless you start with a premise which is true and you reach a conclusion which is false. Okay, moving on. Show that the following are tautologies, and we're going to be using truth table. So you can think of this as one big implication. So here, let's say you have some element alpha, and it implies that you have this big other element, which is beta. Okay. Now, remember that we just saw the truth table for implication, and we just want to try to mimic that. So let's try to build alpha alone and then beta alone. Now, to start off, since we have 3 variables, P, Q, and R, then all the possibilities are going to be 8. P can either be true or false, and Q can either be true or false, and R can either be true or false. So you get you get 8 assignments, 8 possible assignments. Now, for when you're either doing your assignments or doing your exams, try to do it like this. You start off with one element, that's for example P. Remember, we have 8 assignments, so divide 8 by 2, you get 4. So you write 4 truths, then 4 falses, alternating. Then you move on to Q. divide again by 2, you're left with 2. So you write 2 trues, 2 false. 2 trues, 2 false, alternating. And finally, with R, divide by 2 again, 1, alternating, true, false, true, false, true, false, and so on. This way you'll go through all of the possibilities without missing one, and it'll be easier for us to correct. So please try to go with this format. And if you had 4 variables, like let's say you had here W, then for W you would have written 8 trues and then 8 falses. And for P you would have alternated here the 4 trues and then the 4 falses, and so on. You get. Okay, so back to our original problem. Let's first build P implies R, which is easy enough, right? So P implies R, remember, it's only false when you start with P as true and R is false, and you reach that R is false. So you have P is true, R is false, this gives you false, and here as well, all the other braces are true. Now we want to build, we call this beta, we want to try and build it. And it's made up of even smaller elements. So let's grab this guy, try to build it, and grab this guy and try to build it. Okay, so P implies Q, Q implies R. You get the idea of how implication works. And we want the OR between these together. And remember, OR, if one of them is going to be true, then both of them are going to be true. True, 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 true. All of them are true. And finally, we have R alpha and beta. So all we have to do is just do an implication. This is just like a normal implication. You can think of this as some other variable alpha, this is some other variable beta. Simply do the implication between them. And if you do it, all of them are going to be true. So it is a tautology, because remember, what's a tautology? For every possible assignment, it's going to be true. Okay. Moving on. So construct a truth table for these compound propositions. You notice the pause button on the upper right? You're going to be solving this in a second, but I'm going to throw this here first. So you remember how Zoar works, how the exclusive OR works, since we have it here. And I'm also gonna throw in the equivalence, because you have here P is equivalent to not Q. Equivalence literally just means 2 implications. So P is equivalent to not Q, that means P implies Q, not Q, sorry, and not Q implies P. If you have both of these together, that's like you get equivalence. And it's read as P if and only if Q. It's only gonna be true when both elements have the same value. If both of them are true, it's gonna be true. If both of them are false, it's gonna be true. Okay. So take your time and try to do the truth tables for these. Okay, the solution for the first one, the solution for the second. You can check your answers here. As you can see, this guy is not a tautology, but it is satisfiable because you found assignments where it was true. This guy is a tautology, everything is satisfiable. Okay. Moving forward. Consider the NAND binary logical operator. Okay. So the not AND, we're going to give it this symbol in this exercise. Remember, this is Zoar. We're going to give this for NAND. It's defined as follow, not the AND between them. Prove that NAND is commutative. We're going to do this without the truth tables, sorry. So, how can we do it? We want to use equivalence rules. equivalence rules. Like for example, let's say you have A and B. That's equivalent to saying, for example, B and A, because we know that the normal and is commutative. Here we want to prove something else, that the not and is commutative. Another rule you might have is De Morgan's. So if you have not A and B, that's going to give you not A or not B. Okay? So let's see how this works. So we start off with the original statement. We want to prove that P NAND Q is the same as Q NAND P. So we write a question mark. Is this true? First of all, on both sides, we'll just write the definition. What does it mean? This and this. We're just copying, pasting the definition. Step 3, De Morgan's law. So it's kind of like the not, we're gonna be inserting it here. So not P or not Q. Same thing here, not Q or not P. We know that OR is commutative. So flip these guys. Not P or not Q. You have the same formula on the left, same formula on the right. So yes, it is equivalent. Therefore, the whole statement is true, meaning NAND is commutative. Okay. Moving on. Determine whether NAND is associative. Okay. So take your time and try to do this. And there is no one unique solution. So you could have found a different solution for what we did here. We could have simply, for example, here at this line, we know that AND is commutative. So you could have simply said here not P and Q, and you would have been done without needing to use De Morgan. So there is no one unique solution when doing these types of proofs. Ideally, you'd like to go for the shorter solutions. Okay, so try to do it here, but remember we're asking determine whether NAND is associative. We're not telling you to prove that it is, you just have to tell us yes or no. If it is, then you'd want to reach something like this here. If it's not, you want to use a contradiction. Like you can want to find an assignment that works here but doesn't work here. Okay. Go for it. Okay, let's see the solution. Okay, so again, step 1, write the statements. And by the way, I should have maybe mentioned that associativity just means you can move the brackets around. So if it looked kind of weird what you were trying to prove, associativity just means like if you have X and Y and Z, well, we know it doesn't matter which order you do the ANDs. So you could either do these first or these first, it doesn't matter. That's what kind of associativity means. Okay, so step 1, just say just replace Q and R here and replace this guy here. Step 2, just as the implication, you can now assume that this guy is just some element, alpha. So you can now simply try to do P NAND alpha. So it's not P and this alpha. We're similarly doing everything on the right. Same as before, now we're gonna enter the not inside, not P or not this guy alpha. Well, we have 2 nots here, so they can just cancel each other out. and we're doing the same on the other side. We finally reach this. It might not seem as it to you right now, but this is kind of obviously not equivalent because of the structure of it. Hopefully, as you solve more and more exercises of these types, it'll start to be apparent what is equivalent and what isn't equivalent. Okay, so if you go here and give these two different assignments, okay, or sorry, actually the same assignment, P is false, Q is false, R is true, and we try to give it to the right hand and left hand sides, one is going to equate to true, the other is going to equate to false. You can pause and run through how it's done. So no, they're not equivalent. They're not equivalent. That means NAND is not associative. So this is like your first taste of contradiction. We were asked, is NAND associative? This is kind of assuming it. Yeah, let's assume that it is equivalent. If it is, then the left hand has to equal the right hand side. We kept going, and eventually we found a contradiction. We found a counterexample. Yeah, here a counterexample is maybe better words for here, for what we just did here, rather than a contradiction. Yeah, we'll actually see what contradiction means in later recitations. Okay. Moving on. Show that each of the following statements is or are tautologies. So, from what we've seen before, it was kind of easy to read because we had a bunch of brackets, so we knew what we had to do first. Here, it's not as clear. Like, should I do not be and these, and then I should do the implication, or should I do the implication first and then I do it with the and? So before, like for example, in normal mathematics, if you had 2 plus 3, or in basic mathematics, you'd know you'd have to evaluate 3 multiplied by 6 before the addition. You're not going to add 2 and 3 together first. So this is why we're going to be needing operator precedence. So which operator has the highest priority in the order of strength. So you got not is number 1, then and or implication equivalence. So you can think of here not be as like one single element. You have to and it with this guy, and then the result of this, you apply it to Q. You're also going to need the following information. Alpha implies beta is equivalent to saying not alpha or beta. Like both of these statements have the same truth value. This is going to be important when you want to try to solve this. This is another rule of equivalence. Okay. You can pause now and start. Solution time. For the first one, we're going to try to be evaluating the right side first. Sorry, the left side. So, not P and P or Q. We're going to be inserting this into these guys. So you have not P and P, or not P and Q. So that's how you do this distribution. It's also rules of equivalence. Okay. I don't want to say it's exactly like what I'm about to write, but if it's easier for you to imagine, try to seeing it like this. So 2 is your not P, and here you have your P and your Q. So it's like 2 multiplied by 3 plus 2 multiplied by 6. Just to have like a similar idea of how distribution works. These are two completely different concepts, so don't take this as a rule, just try to use this for imagination. Okay. So now what can we do? We will do the rule alpha implies beta, which is not alpha or beta. So you have all of this is your alpha, and this is your beta. And to make it easier, you only need this as your alpha. Why? Because not P and P is always gonna be false. And if you remember, false or anything is gonna be that anything. So not just this small alpha or beta, which is Q. Again, we're gonna insert the not inside P or not Q or Q. If you remember, just like not P and not P is always false, not Q or Q is always true. And true or anything is also gonna be true. That's that. If you couldn't do neither part 1 or part 2, but now you kind of get the idea of how to solve it, you can pause and try to solve the second one. And the solution for the second one is as follows. What did we do? Okay, so first we got rid of the small implication. Again, this is gonna be like your big alpha, beta. So eventually you wanna do your not alpha or beta. But before you can do that, your alpha is a bit messed up, so we wanna fix it. So starting with the smaller alpha or beta, which is P implies Q. We'll do it here. Same distributive law we did before. P, we're gonna insert it into the brackets. You get this. P and not P like before is always false. You're left with the small alpha. Apply the rule, you get this. Same as before. Moving on. Okay, a different taste now. Determine whether the following statements are going to be inclusive or exclusive. Ors. So remember, is it this or is it this? A proposition is either true or false. Law of excluded middle. So a proposition, which is sort of what we've been doing all throughout this recitation, is either true or false. So is this statement, or sorry, is this or inclusive or exclusive? So for example, let's say the Netherlands won the 2010 World Cup. Is this proposition, the statement, can it be both true and false at the same time? No. You either won the World Cup or you didn't, and they didn't. So that's an exclusive or. Tell me, what do you think of this statement? To be on the honors list, you need to have a GPA of 85 at least, or be in the top 10% in your class. Well, it's a normal or. It's inclusive. If you get at least 85, you're in the honors list. If you're in the top 10%, you're in the honor list. If you happen to do both at the same time, you're also going to be in the honor list. An interesting thing to see. So let's say, actually this is interesting. Let's say this is P So you getting 85%. And let's say this is Q. So if P or Q is going to be true, that implies what? R. Right? If you get 85, or if you're in the top 10%, then that implies you're going to be on the honors list. You can go try to relate this with what we talked about later, before, on the implication truth table. Like right now, let's say you got more than 85% and at the same time you were in the top 10%. If you weren't on the honors list, then that doesn't make sense. You've broken the rule. Okay, so if your premise is true and you got a conclusion which is false, you weren't on the honors list, then this doesn't make sense. This is wrong. This is the only time where implication is false. Let's do the first parts, the first two parts. We're going to do them together, and then you will do the last three parts. So we have a bunch of English sentences. We want to translate them into formulae using propositions. So P, you got an A on the final exam. P, you got an A on the final. Q, you participated in class. R, you got an A on the course. So statement 1, you got an A on the course, but you don't participate. So you got an A on the course, but you don't participate. Well, simply it's just two statements that exist together. Hey, you got an A and you don't participate in class. Okay. You got an A on the final, you participated in class, and you got an A on the course. Just three statements that happened at the same time, three facts. Pause here and try to do the last three. Unpausing. You got to get an A on the course, it is necessary for you to get an A on the final. To get an A on the course, it is necessary for you to get an A on the final. What do you think? Hopefully you've already thought so. We have an implication here. It's either going to be P implies R, or it's going to be R implies P. So what does the first one say? If you get an A on the final, then you got an A on the course. If you get an A on the final, then you're going to get an A on the course. Whereas the second one says, if you get an A on the course, then that means you must have gotten an A on the final. The second one makes more sense. You got an A on the course, then that means you must have gotten an A on the final, which is what this statement is saying. To get an A on the course, it's necessary that you got an A on the final. The reason the first one is wrong, because hey, if you got an A on the final, that doesn't mean you got an A on the course. You could have failed the midterm, for example. So, part 4, you get an A on the final, but you don't participate in class. Nevertheless, you get an A on the course. There's no condition, there's no necessary, there's no sufficient. So here it's just a bunch of facts that all happened. You just add them all together. Just a remark. Let's say we have alpha implies beta. we usually say that beta is a necessary condition for alpha, and alpha is a sufficient condition for beta. Does that mean? Well, let's say beta is false, then there's no way that alpha could be true. If alpha is true and beta is false, then the whole formula becomes false. Remember the truth table? This is the only place where alpha implies beta is false. So beta is necessary for alpha. Alpha can't be true if beta is false. However, if beta is true, then alpha could be false. It's not sufficient. If beta is true, it's not sufficient that for alpha. Like alpha could need two conditions for it to be true. Beta was true, but hey, you got another thing that was false. So that's for the necessary. As for the sufficient, well, if alpha is true, then beta has to be true as well for the whole formula to be true. Like alpha is sufficient for beta. Alpha is true, then beta has to be true as well. Because if you write that beta is false, then the whole formula becomes false. So if alpha is true, then that's sufficient for beta to be true as well. But if alpha is false, then that doesn't mean that beta should be false as well. Beta could be true. So alpha being true is sufficient for beta to be true. But hey, if it's false, then that doesn't mean that beta should be false. It could have had another thing that was sufficient for it to be true as well. So if we go to part 5, it is sufficient to get an A on the final and to participate in class in order for you to get an A on this course. Sufficient. So we're talking alpha territory here, and you have something and something, which is your alpha, will give you your beta. So P and Q are sufficient for you to get an A on the course. Okay, moving on. Now let's do it in reverse. I want you to pause the video here and try to come up with sentences for the English equivalent of these guys. Okay, so the sentences, they don't have to make sense. Let's see what we got. So P or Q implies R. P, you got an A on the final, or you participated in class, then you get an A on the course. Easy enough. What about the second one? Not R and not Q. If you don't get an A in the course and you don't participate in class, then you won't get an A on the final. Now, this is the translation. It might not make a lot of sense English-wise, but this is the translation of this formula. So it's kind of like learning a language. So the last idea for this recitation, or last bunch of ideas, converse, contrapositive and inverse. So let's say we have our original statement, which is if P then Q. Remember, this is implication. If P then Q. We have these definitions. The converse is simply flipping the variables. So it's now Q implies P. The inverse says, hey, if not P, then not Q. Now, the contrapositive is adding the negation and flipping the variables. So not Q implies not P. Let's see an example of these. So, your statement, if two angles are congruent, meaning they are equal, then they have the same measure. Sure. Converse, if two angles have the same measure, then they are congruent. So like flipping P and Q. Inverse, if two angles are not congruent, then they do not have the same measure. So here the P and Q stayed the same, but we added the negation. Finally, contrapositive, if two angles do not have the same measure, then they are not congruent. All of these seem to be saying the same thing, right? And all of them are right, like they all make sense. But if we look at another example, if a quadrilateral is a rectangle, then it has two pairs of parallel sides. Makes sense? You have a rectangle, then you have two pairs of parallel sides. Converse, if a quad has two pairs of parallel sides, then it is a rectangle. Well, no, think of a rhombus, for example, or trapezoid, or not trapezoid, I don't think so. So if you have two pairs of parallel sides, then that doesn't mean you are a rectangle. Inverse, if a quad is not a rectangle, then it does not have two pairs of parallel sides. Rhombus. It's false, it's not true. Finally, contrapositive, if a quad does not have two parallel sides, then it is not a rectangle. Makes sense, right? If you're working with some quad and it doesn't have two parallel sides, then there's no way it's going to be a rectangle. The point of this is to hopefully you got this, but the point is your original statement, P implies Q, will have the same truth value as your contrapositive, which is not Q implies not P. The converse and inverse, they could have the same truth value, like here with the angles, but it's not necessary. It's guaranteed that the statement and the contrapositive have the same truth value, but not so much for these guys. This is going to be very interesting because it's usually a trick you could use. If you're, for example, if you're trying to prove P implies Q and you're finding it too difficult, then hey, maybe try to prove not Q implies not P. Then you get the same result as this, and so on. Okay, last exercise for this recitation. State the converse, contrapositive, and inverse of these conditional statements. If it snows tonight, tomorrow we will build a snowman. If it snows tonight, tomorrow we will build a snowman. Well, step one, we need to find our P and Q, or Z and X, or whatever. You need to come up with variables that kind of break down this sentence. So I'm gonna put this on the side so just we remember what we're trying to find. So let's assume C, it snows tonight, and R, tomorrow we will build a snowman. This is our original statement. C implies R. It snows, we're gonna build a snowman. So converse, Q then P. So R then C. If we are building a snowman tomorrow, it will be snowing tonight. You can see here why this isn't necessarily true. It could have snowed tomorrow very heavily, and it didn't snow tonight, and hey, we're going to be building a snowman tomorrow either way. Next is contrapositive. So not Q, then not P. So not R, then not C. If we won't build the snowman tomorrow, it won't be snowing tonight. Yep. If we won't be building a snowman tomorrow, then we definitely didn't snow tonight. Now you might be thinking, hey, there could be other reasons that made us not build a snowman even if it did snow tonight. But you have to look at this as if this statement is law, right? C implies R is law. Like, hey, it snowed tonight, then tomorrow we're going to be building a snowman, even if it was Armageddon or explosions or whatever. If it snows tonight, we're going to be building a snowman tomorrow. It's like a law. So if you didn't build a snowman tomorrow, then it definitely didn't snow tonight. And lastly, the inverse. If not P, not Q. So if not C, not R. If it won't snow tonight, we won't build the snowman tomorrow. Similar reasoning as we had for the converse, like maybe it snowed tomorrow morning very heavily. Okay. Your turn. Pause the video. Do the same steps that we did. First come up with your C and R, then converse, inverse, contrapositive. Okay. 3, 2, 1. This is your solution. So C implies R. It is snowing. It is. Let's actually read this through. Okay, so if it snows too much, I'm gonna catch a cold. Snows too much, then I caught a cold. Converse, if I catch a cold, then it's snowing too much. No, I took a cold shower, for example. Contrapositive, if I don't catch a cold, it's not snowing too much. Makes sense. I didn't catch a cold. Whenever it is snowing too much, well, whenever it is not snowing too much, I don't catch a cold. We wrote it correctly, but as a truth value, same as converse, it's not necessarily true. Okay, so that is it for recitation 1. I hope you guys took as much as you can from this and understood, and I hope that you really did pause when I told you to, because recitations are all about you practicing. So if you don't try to solve these on your own, it's pretty much useless. I could solve 100 problems in front of you. If you could solve at least 1 or 2, it would be more beneficial than that. So I'm going to be sending you a poll at the end of this week, just to get some feedback from you and give you guys a few options on how we can do these recitations for the rest of the semester. They're all going to be convenient, it's just a matter of your preference. Okay. Alright, thank you for listening, and see you in the next one.